So as we did with quadratic equations, equations where the highest exponent is x squared, we're going to solve higher order polynomials, polynomials with higher exponents than 2, using a variety of factoring techniques that we acquired while we were solving those x squared equations. And so one of the common things that we're going to have to do is assess what is the best way to approach a particular question depending on what's in the original problem. So we look at this first one. We are trying to solve for x. We're trying to find the values of x that make this equation work. And so for a factoring technique, the number one thing we have to have is it equals 0 on one side. So I'm going to subtract 27x cubed from both sides as my first step. So we end up with 9x to the fifth minus 27x to the third equals 0. And so now we have to decide what factoring technique is going to work best for us. Now in this case, I can definitely see that there's some undistributing to be done. So my first step always is going to be to try to see what I can undistribute. So I can see that there's a 9 that's in common in both pieces. And I can also see there's an overlap of x to the third as well. And so then left behind inside the parentheses, it's going to be x squared, because 9x to the third times x squared gets me back to 9x to the fifth. And then a minus 3 times 9 gets me back to the 27. And I don't need any x's there since I have all of them that I need on the outside. And so now we're equal to 0. And so I look inside those parentheses, and that's not a factorable expression. X squared is a perfect square, but 3 is not. So I'm not going to be able to factor this any farther, but I am in a position where I'm going to be able to find the solutions to this equation by taking these two pieces and setting them equal to 0. So in the first one, if I just divide both sides by 9, and we just end up with x to the third equals 0, hopefully we can see pretty clearly that one answer for this problem is going to be just x equals 0. If I take the cube root of both sides, the cube root of 0 is just 0, so we've got x equals 0 as one of our answers. Now over here in the other part, I can't factor, but because there's no x term, I can solve by isolating the x squared and taking the square root of both sides. So that's what I'll do. So I'll add 3. So we've got x squared equals 3. So now I take the square root of both sides. And of course we have to remember that we need to include a plus or minus in front of our answer. And the fact that it doesn't work out evenly isn't a problem. We can have square roots on our answers, as we've had plenty of times before. So we get plus or minus the square root of 3. So taken together, our answers to this one are x equals 0 and plus or minus root 3. Now the next one has 4 separate terms of the problem. I've got an a cubed, the 2a squared, the 16a, and then the 32 that's on the other side. So hopefully this jumps out at us as being a factoring by grouping situation. That's really the only type of factoring that we can do when there's 4 parts to the problem. So I'm going to move the 32 over to this left-hand side to set it equal to 0. So I'm going to add 32 to both sides, so I end up with a plus 32 there. And so now I'm going to take that factoring by grouping approach. So I'm going to factor from the first 2 terms of the problem. So I'm going to use a squared as that common piece. So I undistribute an a squared, and so that leaves me with a as the first piece inside the parentheses, minus 2. So a squared multiplying times a gets me back to a to the third. A squared times negative 2 gets me to negative 2a squared. And then for the second half of the problem, I'm going to undistribute. I can hopefully see that 16 divides evenly into both of these. And since I need to end up with the exact same expression inside the parentheses as I did over here, I'm going to undistribute a negative 16. So if I take out a negative 16, that'll mean I've got a as the first piece there. Since if I was to redistribute, that would get me back to negative 16a. And indeed, minus 2 as the second piece, if I was to multiply that by the negative 16 that we undistributed, will get me back to positive 32. And so then I'm still equal to 0 here. So now I'm going to do that third step of my factoring by grouping process. So I've undistributed from the first half, from the second half of the problem. So now I need to undistribute here. So I'm going to undistribute the a minus 2. So imagine that those are gone. And so then I'm left with a squared from the first part and minus 16 from the second part of the problem. And so now I can see that I can factor a little farther. The a minus 2 I can't do anything with, but a squared minus 16, unlike on the previous problem with the x squared minus 3, this time it is a difference of two perfect squares, so I'm going to be able to factor that as a plus 4 and a minus 4. And so now I have a set of just linear factors. There's no exponents on the a's anywhere, so I'm just going to set each of these equal to 0 and solve. So I'm going to have a minus 2 equals 0, a plus 4 equals 0, and then a minus 4 equals 0. And so in the first one, I'm going to add 2 to both sides. So we get, I'll list off my answers over here. I've got a equals 2 as the first of my answers. If I subtract 4 from both sides here, I'm going to get negative 4 as a second answer. And then finally, if I add 4 to both sides in this third part of the problem, I'm going to get positive 4. So I can either list it off as positive 4, or I could just write plus or minus 4, and then I've got my 3 solutions. We can also use regular reverse FOIL techniques on problems that have an exponent higher than 2. So if this problem here was n squared minus 12n plus 27, we would factor it into 2 sets of parentheses. There's nothing that we can undistribute, so we'd have n as the first piece in each set of parentheses, and then we'd be looking for 2 numbers that multiply to make 27 and add to make negative 12. So it'd have to be 2 negatives, and so hopefully pretty obviously that'd be minus 9 and minus 3 as the 2 numbers that multiply to make 27 but then add to make negative 12, and so then we'd set those factors equal to 0. So in this case, I'm actually going to take the exact same approach. It's just that the first piece in each set of parentheses isn't going to be n, it's going to be n squared, because I have to multiply those first 2 terms to make n to the 4th instead of just n squared like it would be under our circumstances before. And as long as the exponent in the middle term is half of whatever is the exponent on the first term, so 4 is the exponent on the first term, 2, half of 4 is the exponent on the second term, then that's an indication that we're going to use this style of factoring. And so once I get to here, I've got n squared as the first piece in each set of parentheses, and then just like we saw on the bottom, I need 2 negatives because I'm multiplying to make 27, but I have to add to make a negative 12, and so that's going to be 9 and 3. And so now at this point, I'm going to keep on factoring whatever I can. That's probably my best bet. So n squared minus 9 is a difference of squares. So I'm going to be able to factor that into n plus 3 times n minus 3. Now the n squared minus 3 is not factorable. We've already seen that before, so we're going to have to solve that piece using square roots after we set it equal to 0. But the bottom line here is we started off with a reverse FOIL step, even though our exponent here wasn't 2, it was something higher. So as long as this second term has half of the exponent size that the first term does, then we're almost certainly going to be able to reverse FOIL this. So from here, I'm going to set my factors equal to 0. So I've got n plus 3 equals 0. I've got n minus 3 equals 0. Then I've got n squared minus 3 equals 0. So if I subtract 3 from both sides here, I get n equals negative 3. If I add 3 to both sides here, I'm going to get positive 3, so this time I'll just list them instead of writing the plus or minus. And then on the last part, I'm going to need to isolate the n squared. So I get n squared equals 3. And now I'm going to take the square root of both sides, just like we did earlier. So we get n equals plus or minus the square root of 3 as my other 2 answers to this problem. In our second example, we have very much the same situation once we move everything over to one side so that it equals 0. So I'm going to subtract 18x squared from both sides. I'm going to add 81 to both sides. So I'm left with 0 over here on the right, Then on the left, I just have my x to the fourth minus 18x squared, and then plus 81. So now I'm set to try to factor it just like I did the previous question, because I can see that my exponent here of 4 is double that, what I see in the middle term. So I'm going to approach this with a little reverse FOIL, where instead of x as being the first piece in each set of parentheses, it's going to be x squared. Now I look and I need two numbers that multiply to make positive 81, but add to make a negative 18 in the middle. So I'm going to have two negatives. So hopefully we can piece together that those two numbers are going to be 9 and 9. So I have x squared minus 9 twice. So I'm going to get the same answer out of both of these sets of factors. Now I can factor again, like we saw in the previous question. I can say x squared, or whoops, we can say x plus 3 times x minus 3 for the first one, and then for the second one it's the same thing, x plus 3 times x minus 3 equals 0. So we've got the same difference of squares in both sets. So we're just going to get two answers on this one. I'm going to set x plus 3 equal to 0, and I'm going to set x minus 3 equal to 0. If these over here were different factors than the ones that I already have, then I would have to set them equal to 0 and solve those as well. But in this case, since it's the same thing twice, I can just go ahead and worry about these two. So we're going to get x equals negative 3, and then if we add 3 to both sides, we're going to get x equals positive 3 as our second answer. So we have two answers to this problem.